cause no confusion. Okay, picking up from where we left over last lecture, remember last lecture we went over the syllabus, we went over definition of some of the terminologies we use in thermodynamics, like system, surrounding, adiabatic versus non-adiabatic, closed system versus open system, etc. And at the end of last lecture, we spent time going over derivatives and also, well, that part of the calculus. So let's just finishing up on how to do integral calculus before we move on to chapter 2. I mean, not chapter 2, before we move on to ideal gas law. So integral calculus is pretty much like derivative calculus. It's just a reverse version of that. So derivative is breaking down your function to like very small pieces, right? Integral is, well, adding them back up. So we know what the total area below the curve is. So in this case, we have two different types of integral calculus. The first one is indefinite. It doesn't tell you what's the specific range we're doing that integral is. It gives you an equation. Or you can have the definite integral, where we give you a range, just estimate what's the area below that curve. Like derivative, there are several useful equations for integral calculus. So these are the things you should already know in your calculus class. Again, I'm not your math teacher. I'm not going to go over them like one by one, but just know where to find it, right? Our exams are open book, open note. So know where to find these equations whenever you need them. But let's do an example together before we move on, just to refresh your memory on integral calculus. So some of the example questions, let's do this one. This one is the 1.65. Like, for example, let's focus on the first one. It's giving you this relationship, like d fx over dx equals to 2 times x to the third plus 3 times e to the 5x. Right, so the question asks you to find out what is fx. So let's do it in this way. Now, first of all, we want to move that dx onto the right-hand side, because otherwise we can't do the integration. So move dx, or the other way to put it is we're multiply dx on both ends. It's the same idea. So it becomes dfx equals to 2x to the third plus 3 e to the 5x dx. And then we can do integration on both ends. So that gives you integration of dfx equals to integration of the 2x third plus 3 e to the 5x dx. And now you know where to use our equations for, right? So in the previous list of the equation, we have the integration of x and dx equals to xn plus 1, n plus 1 plus c, and this n can't be 1. And the same can be negative 1. And let's see, yeah. And this part, the exponential part, we have the exponential of ax dx, where a is a constant. That just equals to e to the ax a plus c. And that plus c just remains as a constant. Right, so solving this integral now becomes a pretty straightforward math problem. Left-hand side becomes fx. On the right-hand side, we have, well, 2 times x to the 4 over 4. And this becomes 1 over 2 plus 3 over 5 e to the 5x over 5 plus some constants. All right, just a calculus problem to refresh your memory. The second part of this question is, well, giving you the integral, can you find out what that original function is? So this one, effectively, we're just taking the derivative of this equation to undo the integration that we show, right? So in this case, the quick answer is just to take the derivative over x of 3x to the 8th plus c. And that's going to give you, well, 24x to the 7th. Pretty straightforward, and you also did some practice calculus problems in your discussion worksheet. There are more practice problems in the chapter end problems, just to refresh your memory on that. All right, any questions on the math part before we move on? No? Okay. Let's move on to our lecture 2. So lecture 2, we start talking about more into thermodynamics. So in this case, we will start talking about temperature, number of moles, and then ideal gas law. And also at the end, we'll move on to talk about more general equation of state. So let's get started. The first one, temperature. So there are several different kinds of definition of temperature. But before we start talking about temperature, there's one rule we have to say. You probably know we have like 3 fundamental laws of thermodynamics. But after the discovery of those 3 fundamental laws, then scientists find out, okay, there's a zeroth law of thermodynamics that must hold true for everything else to be true. So we have to introduce the zeroth law of thermodynamics first. So let's read it together. And also when reading it, think about the definition we went over, right? So 2 systems that are each found to be in isothermal equilibrium with a third system will be found to be in thermal equilibrium with each other. So in this case, now it's a good chance for you to refresh your memory. What is a system, right? So that is a macroscopic part of the universe that we care about. What is thermal equilibrium? That's saying adding a non-adiabatic wall does not change the macroscopic property of your system. So that's a thermal equilibrium. Now the way to put it is, well, the zeroth law basically allows us to use something like a thermometer to give us a measure of the temperature. Now if you think about it, the way we use thermometer, right? You have say a mercury thermometer. You put it in a cup of water that is 100 degrees. You let it to reach a equilibrium, so your thermometer and your first cup of water, or your system 1, are in equilibrium with each other. Now your thermometer and the system 1 have the same temperature, same property. When they say same property, the mercury in your thermometer will have the same volume when it's in the 100-degree water. Right? Now you put that thermometer into a separate cup. Now maybe that cup contains oil, and that oil is also at 100 degrees. Now the thermometer after expansion will show you the same level. All right, so that's how we use the zeroth law of thermodynamics to design a thermometer and then use that thermometer to tell you information about temperature. So a few things about, well, what makes a good thermometer. This is more like a interesting fact we should know, like mercury, why is it so good? Now we want the reference system to always expand when heated. Otherwise, using that thermometer would be very complicated. So mercury is a very good choice. And if you think about it, liquid water is not a very good choice for reasons we will cover when we talk about phase diagram of water. But if you're curious, you can read the textbook. It tells you the reason. So that's the zeroth law of thermodynamics. And then in the second part, we have the more. So this is more like a refreshment of your Gen Chem. Like we have number of moles. We start from the Avogadro number, which is one of the fundamental constant, universal constant we have in our SI unit system. The Avogadro number is defined to be the number of carbon-12 atoms in exactly 12 grams of carbon-12. And then in this section, we have several more definition of terms that we sometimes will use in this class just to make sure you know what their dimensionality is. They look very similar. Like, for example, we have atomic weight or molecular weight. So these two, whenever you see an abbreviation of R, it tells you it is a relative atomic mass or a relative molecular mass. And they are unitless relative properties. We won't use it very often, but just know whenever you see an abbreviation R, that's telling you this is a unitless relative atomic weight. More often, we talk about atomic mass and molecular mass. So atomic mass and molecular mass are the actual physical mass of the atom or molecule we care about. So their unit will be in gram or atomic mass unit, AMU. And then you have the relative atomic mass. So then we have the molecular weight, which is basically the mass divided by the number of moles later on. So just know, like, whenever you see an abbreviation R, that tells you that value is a unitless property, that's all. Next up, we have our chemical amount, so number of moles, and its unit is number of moles. And we also have the relative, well, the molecular weight of that defined as Mi, so that's the relative molecular weight. That's the molecular weight of the species I. So this is the mass divided by number of moles. And this one is obviously in gram per mole. Then we have the mole fraction, which is again a unitless property. So this one is more used whenever we're talking about a mixture. So this is defined as the number of mole of that specific ingredient I over the total number of mole. This part is more like, again, definition and a little bit tedious to my taste, but I want to mention it anyway. Okay, any questions before we move on to talk about ideal gas law? Okay, sounds good, very straightforward. Okay, ideal gases. So first of all, what is an ideal gas? So in the shortest term I can think about is an ideal gas talks about there's zero force between molecule or atoms or particles in general. Right, so these particles or in your ideal gas are just points. It doesn't even have a volume, it's just a point. It has a mass, it doesn't have any interaction with the other atom or molecules in that ideal gas. Now, when talking about ideal gas law, we have pressure, volume, number of moles, temperature involved in there. We went over temperature and the use of thermometer. We discussed the number of moles. And before we talk about the actual ideal gas law, let's just quickly review the units for pressure and volume that we will be using from time to time. For pressure, the SI unit for pressure is pascals, so PA. That's the abbreviation for pascals. So 1 pascal is defined as 1 Newton per square meter. So it's a very small pressure unit. So our SI unit pascal is a very small one. More often in thermodynamics, we use like kPa or megapA. So let's 10 to the 3rd Pascal or like a million Pascal. Or more often we use torr, so that's a pressure exerted at 0 degree by a column of liquid mercury 1 millimeter high with a gravitational acceleration to be 980.665. So torr is just a commonly used unit for pressure, that's all. And you can actually calculate what that torr, you can actually calculate to transfer 1 torr of pressure to Pascal. Right, so we're talking about the column. So pressure equals to, so this is a review of your physics. So pressure equals to force divided by area. And in this case, the force is exerted by the mass of the mercury. So that's mass times your acceleration g divided by area. And your mass is determined by the density times volume times the gravitational acceleration over A. And the volume, because it is in a column, right? So the volume is area times the height. And that gives you density times area times height times G over A. And your A cancel out, becomes density times G times the height. So you can do that calculation and find out that 1 torr of pressure is about 133.322 Pascal. You can check it later on. In addition to torr, we have more units we use. It's a little unfortunate, but we have so many different units, and different people in different fields like it differently. Like you have atmosphere, so that's our atmospheric pressure. That's about 750 torr. And we occasionally also use bar for our unit. So just knowing they're all units for pressure, and we use it in different applications. And for volume, it's slightly more straightforward. Typically, we use it as liter, or that's, I guess, liter or 1 dm third is the most often observed unit for volume in this class. But pressure does have lots of units, unfortunately. Okay, nevertheless, so these are the units for our pressure and volume. So we're finally talking about ideal gas law. So the beginning of our ideal gas law actually started in the 60s and 70s, right? So these started from physical chemists making experimental observation on behavior of gas. Or in this case, where the scientists are making the gas at very low pressure to make sure they have more ideal behaviors. So remember, when we were talking about ideal gas, right? So the gas molecules do not interact with each other. So at high pressure, they have more chance of interacting with each other, so they're less ideal. But at very low pressure and larger volume, there's much less chance your gas molecule interact with each other and thus behave more ideally. So when setting up the experiment, we have 2 different sets of observation that tells us about the relationship of pressure, volume, temperature, and number of moles of these gases when they're approaching ideal gas behavior. So the Boyle's law was performed in 1662. So in this experiment, what we have is plotting pressure, which is P. Its unit is in atm. So when reading any scientific figures, I highly recommend you start from the axis and ask yourself, what is these axes? What's the physical meaning of these axes? And on the y-axis, that's our volume. That's in liter. Right. And the setup of this experiment is conducted for 1 mole of nitrogen gas at constant temperature. So when we're saying at constant temperature, effectively what we're saying is each curve here is measured at a constant temperature. You can have multiple curves on the figure, but each curve will be measured at a constant temperature. Now comparing the shape of the pressure versus volume graph to the y equals to 1 over x graph, we see that they have the same shape. So our observation of the behavior here suggesting the pressure equals to some constant divided by volume at constant temperature and mass. So in this case, K is a constant. We will talk about what exactly is K later on. But right now, let's say K is some random constant. And that constant is going to change when you have different temperature. And that's the Boyle's law. That's just like an experimental observation. And also you can think about how to set up this experiment, right? What we want is constant temperature and constant, well, not change number of mole of gas. So you can have like a cylinder of gas and just put it into a water bath of constant temperature and then measure how the pressure and volume change accordingly. All right, so that's a Boyle's law. That's the first piece of the puzzle. Second piece of the puzzle is a Charles law. So this one, or it's Charles Gay-Lussac law. So that one was discovered later on. Well, actually a much longer time ago, later, about 100 years later. So what they are doing is a thermal expansion of gases. Again, for any scientific figure, we look at the axis first, right? So on the y-axis, now it is the volume, and on the x-axis, that's theta. So this theta it's like temperature, but this one is more like talking about a relative temperature, like degrees Celsius. It's not your Kelvin. So that's why you noted like we have the 0 degrees Celsius in here. So the way they conduct this experiment is keeping pressure constant, and also 1 mole of nitrogen. So the mass of the nitrogen gas is also constant. And what we find out is linear relationship between volume and temperature, right? So that's how we have our Charles law, which is V equals to the intercept A1 plus slope A2 times theta at constant pressure and mass. And then in here, what we find out, or what Charles find out back then, is depending on what's the pressure you have, and you can also take the measurement of all different gases, we find out that these line always intersect at about negative 273 degrees Celsius. And that introduced us to the ideal gas absolute temperature scale. So remember before when we were talking about the thermometer temperature, it's a relative temperature. We're comparing the relative temperature of different objects, right? So now we have a mean to define the absolute temperature. Like it doesn't matter what is the object we care about, these lines always intersect at about negative 273. Or we put it as like the observation is the extrapolation of the low pressure P versus theta in this case of any, well, this one should be low pressure volume versus theta. This is a little update. Of any gas will intersect at the theta axis at negative 273. So then we have our definition of temperature. So the triple point of water is defined exactly as 273.16 Kelvin. So Kelvin, so that's our 0 Kelvin definition. All right. So one of the example question you can think about is now, well, we already know what's the result coming from the Charles law. Can we think about it reversely? Right, let's say in a hypothetical world, we do not know what the absolute zero is, but we give you information about the figure and how the volume change with a relative temperature scale. Can you use those information to estimate what that absolute zero is in a hypothetical world? All right. So this part, this one is a pretty straightforward, simple question that's like play around with the unit and moving turns around. So you can try it yourself and check your answer with the answer key or the chapter end problem. And let's spend more time talking about the ideal gas law. So let's actually go backwards to see how do we get our final ideal gas law as PV equals to nRT from the Boyle's law and the Charles law. Or like let's do a derivation together to get the expression of ideal gas law. So these are the equation we will be using. And let's do it together here. So you think about it as our initial state 1. Let's say we have pressure P1, volume 1, T1, and also some kind of mass, right? And can people in the back see my handwriting? Okay. And effectively, we want it to be our final state, which is state 2, right? So we want it to be P1, P2, T2, V, oh, put it in the same one, V2, T2, and let's keep the mass the same, just to save our energy a little bit. Let's keep the mass the same. But if we look at the Boyle's law and the Charles law, we are nearly always requesting either temperature or pressure being constant. So that means we need to add a hypothetical state in between my state 1 and state 2 so we can use our Boyle's law or Charles law. So that's why we have our state. I'm just going to call it A, or an intermediate state. So let's use our Boyle's law first. So to use the Boyle's law, we want to keep our temperature as constant. So we can use Boyle's law. And then from state A to state 2, we want to keep our pressure constant. So we can use Charles law. Right. You can do it the other way as well, and you can try it yourself. So because the second one, we keep the pressure as constant, so for state A, I know my pressure will be P2. And for the first one, we're keeping the temperature constant, so this one will be P2, T1, and mass is always kept constant. And we don't know what volume is going to be, so it becomes like VA, right? So our T is the same, and our T2 is the same. That's how we set it up. So for state 1, in this process, what do we have? So for Boyle's law, remember what we have is PV equals to some constant K. So that tells us we have P1 V1 equals to P2 VA. This part, just using the Boyle's law, and equals to some constant. Let's not worry about what that constant is, but knowing these two are equal to each other. Right? And then using the Charles law, what do we have in the Charles law? We have volume as a linear relationship with A1 plus A2 times T. Or because it is a linear relationship, if you think about it, it's V over T. So this is dividing both ends. Well, no, not dividing both ends. But if we're thinking about a linear relationship, so we have V over T and some kind of slope. So this slope will always be A2. Or the other way to put it, if we plug in number, we have two different sets, right? So V2 equals to A1 plus A2 times T2. The middle one, VA equals to A1 plus A2 T1. Or in this case, what we have is V2 divided by T2 will always equals to VA divided by T1 equals to A2. Now in this relationship, we're trying to find out what VA is. And we can come back here. So VA, that's equals to T1 V1 divided by P2. And plugging that into here. So as a final result, what we end up with is V2 divided by T2 equals to P1 V1 divided by P2 T1. All right, and then we're just moving terms so that 2 goes with 2, 1 goes with 1. What we have is V2 P2 divided by T2 equals to, well, P1 V1 divided by T1. And that always equals to some constant, assuming it is ideal and constant mass. Right. And the next one is adding the number of moles back into our ideal gas law. So this one is more or less a observation, right? We know that for equal volume of different gases at the same temperature and pressure, they always contain equal number of molecules. Or the other way to put it is like if your number of mole increase, your volume will increase proportionally. So then we have our ideal gas law. We have PV divided by NT equals to some constant. Now this constant is our ideal gas constant. Or we have PV equals to nRT. All right, so our ideal gas law, it's not something like people dream about. It's more coming from experimental measurement, and then we derive the ideal gas law from the experimental observation. We'll come back to it later on. And there are different variations of the ideal gas law. So if we think about it, people can also use the relative molecular weight. In this case, the big M stands for the molecular weight of your molecule. So your PV equals to nRT, thus becomes PV equals to mRT over big M. It's also for ideal gas. Or you can use the density as part of the ideal gas law, and then your pressure will equal to density times RT over big M. And for ideal gas mixtures, later on we'll talk more about ideal gas mixtures. Now you can have multiple ideal gases. The only difference by the mass, the molecular mass of those ideal gases. And then the total number of mole equals N1 plus N2 plus N3, because they don't interact with each other. We're just counting the number of molecules in there. And then you can use the partial pressure version of the ideal gas law. And the type of questions we might have is like, for example, can you find the molecular mass of an ideal gas and given its density and temperature and also pressure? Right, so this kind of equation is more or less just plugging numbers. Like we're using P equals to density times R times T over our molar mass. And then we can rewrite that as molar mass equals to rho RT over pressure. And we know what density is. We know what ideal gas constant is. We know what temperature is, and divided by pressure. So this one, just keep in mind, your temperature need to be translated into Kelvin. 25 plus 273. Right, and this one is just plugging numbers and choosing the right ideal gas constant. Okay, any questions? No? Okay, let's move on to our next part, which is equation of state. So we went over the ideal gas law, right? So ideal gas law is an equation of state. So an equation of state basically say for every specific system, again, system is a part of the universe we care about. Like if we can claim that this system of ideal gas is something we care about, right? So for every specific system, there exists an equation of state. So the equation of state tells you the relationship between pressure, volume, temperature, and the amount of substance. All right, so equation of state just tells you what's the relationship between these properties, between these macroscopic properties. For different kind of system, we have different kind of equation of state. Like ideal gas is PV equals nRT. Now we can have equation state for, say, this eraser. It's just going to be a very different one from your ideal gas. Now, there are different types of equation of state. Like, for example, when we look at something like this, it's called a volumetric equation of state. We're expressing volume as a function of pressure, temperature, and number of moles. Likewise, you can express pressure as a function of volume, temperature, number of moles, express temperature as a function of volume, pressure, and number of moles, etc. But this one is called a volumetric equation of state. Now, if you were to ask to write a volumetric equation of state for an ideal gas, it is going to be V equals to nRT over P. Right, it is a function of temperature, pressure, and number of moles. And remember, it is an experimentally determined equation, like what we use. Both Boyle's law and Charles' law are experimental laws we find. And to take it one more step on simplification, in this class, typically we're looking at systems that are pure and one phase just at the beginning, right? Later on, we'll talk about mixture and also phase diagram, etc. But at the beginning, we're only focusing on pure and one phase system. So then the volume, we can basically take the number of mole out from that equation of state to define molar volume. So Vm, this abbreviation M, is defined as molar volume. It's telling you this is a molar volume. So the molar volume is defined as volume divided by number of moles. So for an ideal gas, we have, again, PV equals to nRT. So your V, molar volume, Vm, well, equals to RT over P. But we live in a real world. So on top of ideal gas, I want to use the rest of the 10 minutes just briefly touch on real gas, and we'll look at more next lecture. So we can also have different types of equation state. Now moving on from ideal gas to real gas, or not real gas, I guess Van der Waals gas. So we can also have different equation of state. Like, for example, we can have Van der Waals equation of state. Right, so you can write it as P, the pressure, plus some constant, AN square, V square, V minus NB equals to nRT. Again, don't try to remember it. I mean, you can find it, and we will give you equation you need. Just know what it means, right? So in this case, the Van der Waals equation tells us it's more real than the ideal gas for two reasons. For the first part, we're talking about gas molecules. will attract each other at certain distances. And on the right-hand side, we're saying the volume we're talking about should minus the actual radii of your molecule, right? So your molecule is not like a volumeless point, rather it has some volume. They can't occupy the exact same space. So it is a slightly more real equation of state comparing to our ideal gas law. Let's look at an example question together regarding the van der Waals equation. So let me copy this down. Oh, that's unexpected. So it can ask you to write the van der Waals equation using the molar volume instead of volume and number of moles. And then the second question is, if we use bar, cubic centimeter, moles, and Kelvin as a unit for your pressure, volume, number of mole, and temperature, what is the unit of your constant A and B? Our first question is just replacing your volume and number of mole with molar volume. So this one just becomes, well, pressure remains the same. And then your N squared over V squared now becomes Vm squared A. And your V minus NB, let's think about it later. And that equals to nRT. Now we want to take care of this part, right? We want to take that number of mole out. So what we're doing is dividing both ends with a number of mole. And then this becomes P plus A Vm squared. V over N becomes Vm, and B over N becomes B, equals to RT. All right. Then the next question is, what is the unit of these constant A and B? So one thing we will keep talking about is that in physics and also in physical chemistry, you can only add two properties together whenever they have the same dimension. Or when we say dimension, is you can only add two properties together when they have the same unit. Right? It doesn't make any sense to have, say, 1 gram plus 1 liter. That's not a well-defined relation. Like, you cannot add two things that are different dimension together. So using that knowledge, this one, we can just write, we can just say like, hey, we know Vm and B have same dimension. Or unit. Right, so we know what the unit for Vm is. It's given in the problem. So the unit for Vm is going to be volume, the unit for volume, which is cubic centimeter, divided by number of moles. And that's going to be the unit for our constant B. Now for our constant A, we want this whole thing, A over Vm squared, to have the unit of P, which in this case is bar. Right, again, that's given in the problem. So for A, we want its unit to be canceled with the Vm squared. So Vm squared would have the unit of cm6 divided by more seconds. So A, you want to cancel that out, and times bar. Right. The most important take-home message for this practice is you can only add and subtract two properties when they have the same unit or same dimension. All right. So that's the ideal gas law and also our van der Waals gas. But we're not gonna, I don't have time to finish it, so I just wanna briefly mention what to expect on Friday. So for any equation of state, now assuming it's like one phase and pure substance, we have three different properties interconnected with each other. For example, we have our molar volume, we have our pressure, and we have our temperature. So we have these three internal properties interconnect with each other. Now the equation of state describes the relation of them. The next class, we will talk about these partial derivatives and see how can we use calculus as a tool to understand how many different relationships are there when we only have three variables, right? So we have three things interconnect with each other. How many partial derivatives